Alright, so I know I haven't made a video in forever, but I guess I'll make one right now. Um, Obviously, school started back up, so I'm going to be focused on that, and I'm going to try to do topics related to what I'm studying, which is circuits, quantum mechanics, and more electricity and magnetism. So, to start, we're going to try to derive Schrödinger's equation, which is this equation that I've boxed in red. Very famous one. And I don't know if you'd call this a technical derivation per se, but it kind of gets the point across in terms of what my professor wants. And it starts just with energy. That total energy is your kinetic energy plus your potential energy. Something we've seen in Mechanics 1, which can be rewritten as, well, kinetic energy we know is 1/2 mv squared. And potential energy, I'll just write u of x. And I'm not going to keep writing u as a function notation just because I'm lazy. But u is only a function of x, or a one-dimensional potential in terms of position, whether that's x or y or what have you. Now, we've seen that... Sorry about that. I'm not feeling very well. Momentum, we know, is equal to mass times velocity. And if you square momentum, that's equal to m squared over v squared, or m squared times v squared. And if you do momentum squared divided by 2m, you get 1/2 mv squared, which is kinetic energy. And we can substitute that here. So your energy is equal to, I'm just going to write it in terms of momentum, p squared divided by 2m plus, again, I'm just going to write it as u. And I will be right back. Had to blow my nose. And I'm too lazy to cut it, so we're just going to keep going. Okay, so that's all great. The next thing we need to do, and this is just coming from the wave nature, the wave-particle duality, is we're going to have a wave function, which we'll call psi, which is equal to e to the power of I kx minus omega t. So this is a wave. You could think of this with your sines and cosines. You could expand this out if you wanted. But this is an equation that describes our wave. And if we take the derivative of this with respect to x, what happens? Well, your I and k are going to come down. This is a partial with respect to x. And then it's an exponential, so these are actually really easy to do when we're doing the derivative. And this part is just psi. So I could say this whole thing is just I, k, psi. And I could take another derivative. I could take a second derivative of psi with respect to x. And you're basically going to get the same thing. You're going to get I squared, k squared, and we're going to get our wave function back. The only difference is we're going to be multiplying by another factor of I and k. And I, of course, is an imaginary number, the square root of -1. And if you squared I, that's just -1. So that's all that is. K, on the other hand, I think is normally called the wave number, which is 2 pi divided by lambda, which is the wavelength. And from de Broglie's wavelength, we know, I think that's how you pronounce it. Is it de Broglie? I don't know. Someone will correct me if that's incorrect. I know that's very common. People make a mistake of that. Your wavelength is equal to Planck's constant h divided by the momentum p. Okay? So I could actually take this and substitute it in here. And we can see k is related to the momentum. So k then, if we just plug that in, is you still have your 2 pi, divide by h, multiply by p, which you could also think as p over h bar. This is the reduced Planck constant. Planck's bar is Planck's constant divided by 2 pi. Okay. So we have this, and let's look up here. Let's look at our second derivative. We can rewrite this. So second derivative of psi with respect to x. I squared we said is -1, so I'm just going to put a negative out front. And k squared, well, that's just going to be p squared over h bar squared times the wave function. So if we just square this, we square this, and then we plug it in here. So that's what that is. Now we're going to do a little bit of algebraic manipulation. We're going to multiply over by negative h bar squared. Nothing wrong with that. The second derivative of our wave function with respect to x is equal to the momentum squared times psi. So now, with this in mind, we can actually plug this into our main equation we had earlier. Because if we go back to our equation, or actually not there yet, I have to do something. So we have E equals p squared over 2m plus our potential. I'm going to multiply through by our wave function psi. So we have E psi. This is just from before. We're just multiplying by psi. Momentum squared divided by 2m times psi plus our potential energy times psi. Now this box part, p squared psi, is right here. So I could just put the left-hand side into it. So we have E psi equals minus h bar squared over 2m. And then we just are going to have our second derivative of psi with respect to x plus u times psi. Okay. Now what we're going to do is we're going to do a few things, but the first thing we're going to do is we're going to look at our wave function, and we're going to take the partial this time with respect to time. Now if we go back up to our wave function here, if we take the derivative of that with respect to time, we're just going to get minus I omega, because we're just doing it with respect to time, x is a constant, times our wave function. So this is just going to be minus I because of the negative. The omega comes here, and we're going to get our wave function back. Now this is important because energy, we know from Planck, is equal to h times the frequency, which is equal to h bar omega. And in particular, I want to look at when our energy is equal to h bar omega. Now what I want to do is, it's hard to see right now, but this isn't that far off from this. And I'm going to start by multiplying both sides by the wave function. And now it's starting to look really close because we have an omega, we have a psi. The only difference is there's a negative I squared on both sides. So we're going to divide by h bar because there's not an h bar on that side. And we're going to multiply both sides by minus I. Okay. So when we do that, we get minus I over h bar energy times the wave function is equal to minus I omega psi, which means that this is equal to the partial derivative of psi with respect to t. That is from here. We can see this part and this part. Okay. So now with that, I'm going to solve for E times the wave function. And I'm doing that because that's what we have here. So I'm going to replace this with something else. So that's going to be equal to h bar, and then we're going to have divided by negative I. But if we divide, that can just be moved up. So it's I h bar. So I'm just using our exponents. The parcel of psi with respect to time. And now we can plug this into here. And we're going to get on the left-hand side I h bar, the second derivative of our wave function with respect to time, is equal to minus h bar squared divided by 2m. And I'm just going to rewrite this second derivative as the Laplacian of our wave function, and plus u psi. And this is the Schrödinger equation. I will probably want to memorize this in this course. And one good way to do that is just derive it a couple times. So I was able to derive it today, and now I derived it for you guys, and maybe I'll do it more. So nothing too complicated, just having to know what to do. And that's how you get the Schrödinger equation, making sure I didn't make any mistakes. Looks good to me. All right, so that's everything for now, and I'll